Every time you open an AI app, charge an electric vehicle, or hear about the next breakthrough in military technology, you are witnessing the rise of a new global power struggle. But the real battlefield is not in Silicon Valley, Wall Street, or even the semiconductor factories dominating headlines today. It lies deep inside chemical refineries, toxic extraction zones, and supply chains built around a small group of obscure minerals most people have never heard of. A hidden industrial system now determines who can manufacture advanced weapons, dominate clean energy, and control the future of artificial intelligence. And at the center of that system, one country holds an overwhelming strategic advantage. How did rare earth elements become one of the most powerful geopolitical weapons of the 21st century? And why are nations suddenly racing to break free from a supply chain they allowed to form over decades? Welcome to Elephanta Insights. We uncover the hidden systems driving global conflict, technology, and economic dominance. If you want sharp geopolitical analysis beyond the noise, make sure to like, share, comment, and subscribe. With that context established, let's begin our analysis. The global economy has entered a period of profound structural transformation defined by the dual imperatives of the energy transition and the digitization of the industrial base. Artificial intelligence, advanced robotics, electrification, and next-generation military systems all rely upon a foundational suite of chemical materials known as rare earth elements. Across the world, billions of dollars are being poured into the intangible realms of algorithms and data. Yet, the physical manifestation of this digital future is bottlenecked by highly specialized permanent magnets and intricate solvent extraction techniques. The capacity to build everything from stealth fighter jets to offshore wind turbines relies on an obscure and highly complex chemical refining process. Today, a single nation controls the overwhelming majority of this processing capacity, granting it structural leverage over critical nodes of the global technology system. To understand how this hidden system emerged and why a specific group of minerals has transitioned from a free trade commodity into an active tool of economic statecraft, we must look at the materials themselves. Rare earth elements are a group of 17 chemically similar metallic elements. They are generally divided into light rare earths, such as neodymium and praseodymium, and heavy rare earths, such as dysprosium and terbium. A pervasive misconception is that these elements are geologically rare. In truth, many are relatively abundant in the Earth's crust. Their rarity derives from their intricate geochemical behavior. Bound together in complex mineral structures, they are notoriously difficult, environmentally hazardous, and capital-intensive to separate into purified individual elements. Because few other materials replicate their unique magnetic, luminescent, and catalytic properties at similar performance levels, rare earths are strategically vital even when used in minute quantities. That geological reality was later shaped by deliberate historical decisions. In the 1980s, global production was geographically diverse, with the United States Mountain Pass mines serving as a major supplier. However, beginning in the late 1980s and early 1990s, the Chinese government identified rare earths as a strategic industry, deploying state support, favorable policy treatment, and low-cost financing. Crucially, China was willing to absorb the extreme environmental costs associated with chemical refining. As Chinese producers flooded the global market with low-cost processed materials, Western producers, constrained by stricter environmental compliance and higher operating costs, steadily lost competitiveness. When regulatory pressures hit Mountain Pass in the late 1990s, U.S. production declined sharply, allowing China to deepen its position. Following its accession to the World Trade Organization in 2001, China progressively shifted from raw materials supply toward higher-value downstream processing and manufacturing, a strategy later reinforced by the 2021 creation of China Rare Earth Group. These historical developments created the immense vulnerability of the modern era. The true strategic choke point does not stem primarily from a shortage of raw mining operations, but from highly concentrated midstream chemical separation and downstream manufacturing. According to the U.S. Geological Survey, China accounted for nearly 70% of global rare earth mine production in 2024. Yet its far greater leverage lies downstream. China controls more than 90% of processed rare earths and rare earth magnets globally. However, this dominance conceals a critical vulnerability. To feed this vast processing ecosystem, Beijing has increasingly outsourced the highly toxic extraction of heavy rare earths, such as dysprosium and terbium, to politically unstable, militia-controlled regions across the border in Myanmar, historically sourcing upwards of 70% of its heavy rare earth feedstocks from these areas. Extracting raw ore is industrially insufficient without chemical separation, a process demanding deep technical expertise and the capacity to manage hazardous waste streams. By dominating key stages of magnet production, China exerts decisive influence across the wider industrial ecosystem, effectively drawing the world's raw materials into its processing base before redistributing them as finished components. This immense economic advantage has now crossed into active strategic confrontation. The dynamic between Washington and Beijing has transcended traditional trade disputes, becoming a broader struggle over the commanding heights of technological power. In early 2025, the United States progressively tightened restrictions on advanced semiconductor technology and escalated the trade war with sweeping tariffs. In response, Beijing turned to an asymmetric form of economic statecraft rooted in downstream material dependency. Following licensing requirements for gallium and germanium in 2023, China retaliated in April 2025 by imposing export controls on 7 categories of medium and heavy rare earths, severely affecting associated magnets. Later, China expanded this framework with sweeping extraterritorial provisions. However, following an October 2025 bilateral summit between the U.S. and Chinese administrations in South Korea, a temporary diplomatic truce was reached. Consequently, on November 7, 2025, China's Ministry of Commerce officially suspended its extraterritorial 0.1% to minimize rule, temporarily de-escalating the standoff. That diplomatic truce quickly fractured at the start of 2026. On January 1, Beijing expanded its import-export licensing catalog, expanding the scope of strict oversight to include rare earth compounds of samarium, gadolinium, and lutetium. Days later, on January 6, China introduced targeted dual-use export controls affecting Japan. This legal architecture was further fortified on March 1, 2026, when a revised Foreign Trade Act came into effect, granting Beijing enhanced authority to penalize noncompliance. Crucially, the suspension of China's extraterritorial 0.1% to minimize rule is only temporary, with enforcement now officially scheduled for November 10, 2026. This intact legal architecture provides Beijing a persistent, codified basis to disrupt sensitive allied supply chains under the banner of national security. The consequences of this confrontation extend far beyond trade statistics. Technologically, restrictions on heavy rare earths strike directly at high-performance industrial applications. Without reliable access to elements such as dysprosium, terbium, and now samarium, the deployment of advanced robotics, aerospace systems, and electric mobility becomes vastly more difficult. In response, Allied nations escalated their public-private interventions throughout 2026. The United States augmented its strategic stockpiling with aggressive new industrial policy mechanisms, including guaranteed government offtake agreements, price floors set at $110 per kilogram for neodymium-praseodymium, NdPr, and the launch of Project Vault. A $134 million Department of Energy commitment was also made in June 2026 to recover rare earths from unconventional waste. To secure alternative supply chains, Washington established new bilateral frameworks with Australia, Japan, Malaysia, and Saudi Arabia. Simultaneously, the European Union activated aggressive countermeasures through the Critical Raw Materials Act. In Asia, Japan continues to finance alternative supply chains following the January 2026 export restrictions, while India drastically accelerated its domestic capacity with the February 2026 announcement of dedicated rare earth corridors spanning 4 states alongside a massive magnet manufacturing subsidy scheme. These shifting dynamics present multiple plausible futures for the coming decade. In a scenario where China maintains its dominance, Beijing could retain an overwhelming share of refining capacity by 2035, using its scale, pricing power, and accumulated process expertise to undercut emerging Western projects. A second scenario involves partial diversification, in which sustained Western subsidies and allied industrial coordination establish viable processing hubs in Australia, North America, Japan, India, and Europe, reducing but not eliminating China's centrality. A third pathway depends on technological breakthroughs, such as the mass commercialization of rare earth-free magnet alternatives or major advances in recycling, which could structurally reduce dependence on newly mined supply. A fourth, highly disruptive scenario would involve a major geopolitical crisis over Taiwan, producing sanctions, export stoppages, and severe supply disruptions across defense and semiconductor industries. Finally, a formalized critical minerals alliance could emerge among advanced economies and major producer states to coordinate long-term offtake, investment, and strategic stockpiling, thereby weakening the existing concentration of power. Ultimately, this case reveals a profound shift in how global power operates in the modern era. The weaponization of rare earths demonstrates that geoeconomics has become inseparable from geopolitics, and that control over deep-tier physical supply chains is an increasingly effective non-kinetic tool of statecraft. The popular narrative that digital intelligence exists in an abstract, intangible cloud obscures the reality that advanced computing and clean energy systems remain anchored in physical industrial dependencies. The electric vehicle, the stealth fighter, and the artificial intelligence data center all trace their capabilities back to chemical plants, refining systems, and magnet supply chains. As the world transitions toward clean energy and advanced computing, strategic sovereignty will be shaped not just by a nation's ability to design the future, but by its physical capacity to process the materials required to build it. If you learned something valuable today, don't forget to subscribe to the Elephanta Insight and stay tuned for more insightful content. Goodbye, see you in the next video soon.